In this video, we're going to be talking about Stokes Theorem. So Stokes Theorem is actually just the three-dimensional version of the circulation form of Green's theorem. So just to remind you, Green's theorem, we have our line integral over our curve C, and we take the dot product of our vector field F with dr, and Green's theorem says that this is the same as the double integral over our region R of the partial derivative with respect to x, with g with respect to x, minus the partial derivative of f with respect to y. So we're just going to extend this into three dimensions. So what happens is our region R becomes an oriented surface in R3, and we have to maintain this orientation. So we have the fact that our orientations of our surface S and our curve C, they must be consistent. And then we also need to use the right-hand rule to figure out our normal vectors to our surface. So basically what the right-hand rule says is if you take your right hand and your fingers curl in the positive direction of your curve C, then your right thumb points in general into the direction of your normal vectors. So if I curl my right hand around this curve C, my thumb should point toward the direction of my normal vectors to this surface. So if that's the case, you could think of them as just coming out of the surface like this. So those would be our normal vectors to our surface. Alright, so now we're ready for Stokes' theorem. For our surface S, which is an oriented surface in R3, and for a smooth closed boundary curve C, enclosing this surface S, we have the following: that our line integral over our smooth curve C of our vector field F dotted with dr is the same as our double integral over our surface S, and the integrand here is going to be the cross product of our del operator from the gradient crossed with our vector field F dotted with our normal vector. So n is our unit vector normal to our surface S. In order to use Stokes' theorem, we need to first focus on how to find our normal vector to our surface. So depending on how our surface is defined, either explicitly or parametrically, in either case we're going to find the normal vector by taking the cross product of vectors tangent to our surface in different directions. So to just focus on the explicitly defined surface, we have our surface in terms of x, y, z, where z is described as a function of x and y. So if we take the tangent vector with respect to x, we're going to have 1, 0, z with the partial derivative of z with respect to x. Similarly, the tangent vector with respect to y is going to give us 0, 1, partial derivative of z with respect to y. So now to find the cross product of these two to get our normal vector, we just fill in our determinant here, 3×3 determinant with these tangent vectors. And once we compute this cross product, the result is going to be the vector negative z sub x, negative z sub y, comma 1. So this is our n. This is going to be our normal vector for our explicitly defined surfaces. I'm going to, in the very next frame, give you a summary of how to find your normal vector so that you don't have to compute this every time. Okay, so this is a list of the normal vectors for particular surfaces if you have a cylinder, cone, sphere, or paraboloid. And if your surface is defined explicitly, you have your normal vectors here on the left, and then if your surface is defined parametrically, this would be the form of your normal vectors here on the right. Now let's go ahead and take a look at this example where our vector field is 0, negative x, y, and our surface is defined as the upper half of a sphere, x squared plus y squared plus z squared equals 4, and then the boundary of our surface is the circle x squared plus y squared equals 4 in the plane z equals 0, or in the xy plane. Now just to remind you, here's our Stokes theorem, and so for this theorem we're going to have to use, or in this calculation, we're going to need the cross product between our del operator and our vector field f. So let's start there. So our vector field was 0, negative x, y. So when we take the cross product here, we're going to take the partial derivative with respect to y of y minus the partial derivative with respect to z of negative x. And that's going to give us our I component. Minus the partial derivative with respect to x of y minus the partial derivative with respect to z of 0. and that's our j component. And then lastly, plus the partial derivative with respect to x of negative x minus the partial derivative with respect to y of 0, and that's our k component. So simplifying, let's see what we get. With respect to y, we have 1. With respect to z, we have 0, so 1 minus 0. I minus, with respect to y here, we have 0. With respect to z, 0. So 0j plus our partial derivative with respect to x, negative 1 with respect to y, 0. That's k. So we end up with the vector 1, 0, negative 1. So then now we're going to find the normal vector and dot it with this result. Okay, so now we've found the cross product and we're going to dot that with our normal vector. So for n, if we go back to just a moment ago, we discussed for a sphere that the normal vector was of the form x over z, y over z, 1. So we can use this, and we'll take the dot product of these two for our integral. So we have the double integral of 1, 0, negative 1 dotted with x over z, y over z, 1. Okay? And then we get, as a result here, double integral is going to be x over z plus 0, and then negative 1 times 1, so minus 1. Alright, now we just need to define our region over which we're integrating. Now that we've evaluated our dot product, we're actually integrating over region R. And so what we're going to do here is we're going to convert to polar coordinates in order to make this integration easier. So we have over here the conversion to polar coordinates. So what that gives us is our double integral, and we have r cosine theta. And if we solve our surface for z, we're going to end up getting square root of 4 minus, and then it's going to be x squared minus y squared, but that's equal to r, so minus r squared. And then we have negative 1, or minus 1, and then r dr d theta for our substitution. However, I'm going to integrate with respect to theta first because it's going to make the rest of the integration easier. So with respect to theta, our surface or our region varies from 0 to 2 pi, and then our radius varies from 0 to 2. Okay, so distributing this r, we end up getting, and this double integral is going to become r squared cosine theta over r square root minus r, and we're going to first integrate with respect to theta. So every r is a constant here. This then leads to the following. We have r squared over r square root, and then the integral of cosine is going to give us sine theta, and then minus r theta. Okay, and then we'll evaluate from theta equals 0 to 2 pi. Now evaluating this integral at our boundaries for theta, sine of 2 pi and sine of 0 is both 0, so this whole entire term goes to 0, and we just end up with our integral from of negative r times 2 pi. Then we're going to integrate with respect to r. Our boundaries for r were from 0 to 2, so we end up getting negative r squared over 2 times 2 pi, evaluated from 0 to 2. Simplifying, we get negative r squared pi from 0 to 2, and finally we get negative 4 pi as our answer.